What if the true significance of Google's latest quantum processor wasn't its speed, but the possibility that it is interacting with a layer of reality we barely understand? When Google revealed its advanced quantum chip in late 2024, the headlines focused on a remarkable achievement. The processor completed a specialized computational task in only a few minutes, while a conventional supercomputer would require an unimaginably long period of time to perform the same operation. The comparison was so extreme that it sparked a deeper question among scientists and technology enthusiasts alike. The question wasn't simply how quickly the machine produced an answer. The real mystery was how such a calculation could be carried out at all. Traditional computers process information using bits that exist as either 0 or 1. Every calculation follows a defined sequence of logical steps. Quantum computers operate under very different rules. Their quantum bits, known as qubits, can occupy multiple states simultaneously, allowing them to explore vast numbers of possibilities in ways that seem impossible from a classical perspective. This strange behavior has led some researchers to revisit one of the most fascinating ideas in modern physics: the possibility that quantum phenomena are connected to multiple versions of reality. The processor itself appears surprisingly ordinary. It is not a giant machine built to resemble science fiction technology. Hidden within carefully engineered systems and cooled to temperatures colder than outer space, the device relies on delicate quantum effects that can only survive under extremely controlled conditions. Yet the results it produced captured worldwide attention. In a benchmark designed to test quantum computational power, the processor generated an outcome that would be extraordinarily difficult for classical systems to replicate. The numbers involved are so enormous that they challenge common intuition. They suggest a form of information processing that behaves fundamentally differently from anything humanity has previously built. To understand why this is important, it helps to look at how quantum systems work. When many qubits become linked through a phenomenon called entanglement, they create a mathematical landscape of possibilities that grows at an astonishing rate. As more qubits are added, the number of potential states expands far beyond what ordinary computers can efficiently track. This raises an intriguing question. If a small quantum processor can manipulate a space of possibilities so vast that classical machines struggle even to describe it, what exactly is occurring during the computation? Some physicists argue that the answer lies entirely within the mathematics of quantum mechanics. Others point toward a more radical interpretation. According to the many worlds interpretation, every possible quantum outcome exists within its own branch of reality. Rather than one outcome replacing all others, every possibility continues along a separate path. In this view, reality constantly divides into countless versions of itself. Although this idea sounds like science fiction, it emerged from serious attempts to understand the equations governing quantum behavior. Within this framework, quantum computation becomes especially intriguing. A quantum processor appears to evaluate many possible paths at once before interference amplifies useful outcomes and suppresses less useful ones. The final answer emerges from a process that has no direct equivalent in classical computing. Supporters of the many worlds interpretation have suggested that quantum computers may be exploiting structures that extend beyond a single classical description of reality. Not by opening portals or communicating with alternate worlds, but by operating according to physical principles that naturally involve many possible states existing simultaneously. Whether that interpretation is correct remains one of the biggest unanswered questions in physics. What makes the discussion so compelling is that quantum computers transform these philosophical debates into practical technology. Machines built in laboratories are now performing calculations that force researchers to think more carefully about what quantum mechanics is truly describing. The mystery becomes even more interesting when considering quantum interference. During a quantum computation, different possibilities interact with one another, strengthening some outcomes while canceling others. This process guides the system toward useful results and is one of the key reasons quantum computers can outperform classical machines on certain tasks. No experiment has proven that parallel universes are real. Many scientists remain skeptical of that interpretation and favor alternative explanations. However, advanced quantum processors have made the debate more relevant than ever. As quantum technology continues to improve, humanity may discover that computation itself reveals something profound about the nature of existence. Whether the answer involves multiple realities, deeper mathematical structures, or an explanation not yet imagined, one thing is becoming increasingly clear. Quantum computers are not merely faster versions of traditional machines. They are tools built upon some of the deepest and most mysterious principles known to science. While the discussion surrounding parallel realities captures the imagination, the most significant achievement of Google's quantum processor may actually be far more practical. For decades, one of the greatest obstacles in quantum computing has been instability. Quantum information is extraordinarily fragile. The smallest disturbance, a tiny vibration, a trace amount of heat, or even stray electromagnetic radiation, can disrupt a qubit and destroy the information it carries. This vulnerability has limited the power of quantum machines and prevented them from reaching their full potential. Scientists refer to this problem as quantum decoherence. Unlike traditional computer bits, which remain relatively stable, qubits must maintain delicate quantum relationships throughout a calculation. The challenge becomes even greater as more qubits are added. Increasing the size of a quantum system often increases the likelihood of errors, creating a difficult balancing act between power and reliability. For years, researchers faced a troubling reality. Building larger quantum processors theoretically increased computational capability, but it also introduced more opportunities for mistakes. A machine with enough qubits to solve meaningful problems might become too unstable to function effectively. This is where recent advances have attracted serious attention. Engineers have been developing methods that allow quantum information to be protected through sophisticated error correction techniques. Rather than relying on individual qubits alone, these systems distribute information across larger quantum structures, making it possible to detect and correct certain errors before they ruin a calculation. The significance of this progress cannot be overstated. A quantum computer that successfully reduces errors while increasing in size represents more than an incremental improvement. It suggests a pathway toward practical, large-scale quantum computing, a goal that researchers have pursued for decades. If such systems continue to improve, they could eventually tackle problems that remain beyond the reach of even the most advanced classical supercomputers. Potential applications stretch across many fields. In medicine, quantum simulations could help scientists understand complex molecular interactions with unprecedented precision. New drugs and treatments might be developed more quickly by modeling biological systems that are currently too complicated to simulate accurately. In materials science, researchers could design entirely new substances with properties tailored for specific purposes. Stronger materials, more efficient batteries, and advanced energy technologies could emerge from calculations that are currently impossible to perform. Financial institutions may use quantum algorithms to analyze enormous numbers of variables simultaneously, improving risk assessment and optimization strategies. Logistics networks could become more efficient by solving highly complex scheduling and routing problems. Yet despite these practical possibilities, quantum computing continues to raise deeper questions about the nature of reality itself. Every successful quantum computation depends on preserving quantum states long enough for interference and entanglement to perform useful work. During that brief period, the system behaves according to rules that differ dramatically from everyday experience. Objects in the ordinary world appear to possess definite properties. A light switch is either on or off. A coin shows either heads or tails. Cause and effect seem straightforward and predictable. Quantum systems do not always follow those expectations. Before measurement, a quantum state can exist as a combination of possibilities. Entangled particles can exhibit correlations that appear impossible from a classical perspective. Interference patterns reveal that different possibilities influence one another in ways that challenge common intuition. These phenomena have been confirmed repeatedly through experiments. What remains uncertain is how they should be interpreted. Some physicists view quantum mechanics primarily as a mathematical framework for predicting observations. In this perspective, the equations work extraordinarily well, and no deeper explanation is required. Others believe the mathematics points toward a more profound structure underlying reality. The many worlds interpretation is only one attempt to explain these mysteries. Other interpretations propose hidden variables, wave function collapse mechanisms, or entirely different conceptual frameworks. Each seeks to answer the same fundamental question: what is really happening beneath the surface of quantum phenomena? No consensus has emerged. That uncertainty is what makes modern quantum computing so fascinating. Every improvement in quantum technology allows scientists to probe deeper into behaviors that were once confined to theoretical discussions. Machines operating on quantum principles are transforming abstract questions into experimental realities. As processors become more powerful, researchers will gain new opportunities to test ideas about information, measurement, and the fundamental architecture of the universe. Perhaps the greatest lesson from quantum computing